Pre-Calculus, Chapter 6, looking at vectors, and in this video we want to look at some of the algebra or the arithmetic of vectors. And the first thing we're going to look at is the magnitude. The magnitude of a vector is sometimes, or is also called, the absolute value of the vector. And in a lot of textbooks it's denoted by the absolute value of v. Remember we talked about the letter v being used as the vector. And in some textbooks you'll see a double line here, but and in this book it interchanges those. So sometimes you'll see a single absolute value symbol, sometimes you'll see a double, but both are talking about the same thing, the absolute value of the vector, or the magnitude, the length of that arrow. Now, this will always be a non-negative real number because it's the length of the arrow, and length can never be negative. And its magnitude is not in and of itself a vector, but it's just giving us the length of the vector, and it really is simply a direct application of the distance formula. If a vector is given, the components of the vector are given as ab, then the magnitude of the vector is simply the square root of a squared plus b squared. So let me show you very quickly why this actually works. You remember the vector is from the origin out here to a point AB. Okay, and we want to know the length of the arrow. Well, if you draw a line vertically down, this side from here to here is A, this is from here to here B, it's a right triangle, this is the magnitude. Well, a squared plus b squared equals the magnitude squared, take the square root, and that's where this comes from. So it's simply an application of a right triangle. And again, this is going to be very important as we get to the trigonometric aspects of vectors. So the magnitude of the vector, if you have the components, and that's the key, if you have the components, is simply the square root of the a component squared plus the b component squared. And because we're squaring these numbers, that will always be always be positive, so it doesn't matter if either of the components is negative because you're squaring it, and that's why you're never going to get a negative number. The important thing here, as I said, and I'm restating it, is you have to know the components. So like any math problem, we always start off by giving you the components, and then later on in the problems we don't give you the components, but we give you the information by which you can figure out the components. And so that's where the difficulty or the more challenging problems come from, is you have to remember things from your past, things you've done in the past, in order to figure out the components, so that you can then calculate the magnitude. The math or the arithmetic itself is not that challenging, as you can see. So real quickly, an example, if we're given the point -2, -2, and the point 3, 4, and these are the points of the vector PQ, what's the magnitude? So again, we're in that situation where we need to have the components. So we're going to use head minus tail to figure out the components. Now, the ray is PQ, so P is going to be my initial or my tail, and Q is going to be my head. And so to figure out the components, I do head minus tail. So 3 minus -2 is 5. 4 minus 2 is 2. So these are the components of the vector PQ. Now I can figure out the magnitude by taking the square root of the a component squared, which is 25, plus the b component squared, 2 times b is 4. So the magnitude of this vector is the square root of 29. And we're going to leave all our answers in radical form, simplest radical form if you need, unless we're asked for a particular measurement. So this should be the square root of 29. So again, the magnitude of the vector is quite easy application of the distance formula, and then you're just going to have to apply the head minus tail rule, because you have to have the components in order to do the vector, or in order to do the magnitude of the vector. Real quickly, we're going to look at the adding of two vectors. When you add two vectors together or more, the sum of those is called the resultant vector. And so again, this is going to be a term that you're going to hear quite a bit, especially in word problems. They're going to ask you, what's the resultant vector? And it's simply an adding of two or more vectors. And in order to add components or add vectors, you simply add the components. You add the a component of one to the a component of the other, and then the b component of one to the b component of the other. Let me see if I can't clean this up a little bit. Nah, that's all messed up, so Okay, so if I wanted to add vector u plus vector v, I simply add the a of u plus the a of v, and then the b of u plus the b of v. Okay, so very simple. If I want to add vector u and vector v, I simply add -1 and 4, those are the a components, and then I add the 3 and the 7, those are the b components, so the resultant vector is the vector 3, 10. Another type of arithmetic that will involve vectors is multiplying the vector by a number. Now, when we do this, that number is called a scalar. So a scalar is simply a number that you're going to multiply a vector by. And in order to multiply by a scalar, it's kind of like the distributive property. You simply multiply each component by the scalar. So if you take the product of a scalar k and a vector u, you're simply going to multiply the k, the scalar number, times the u component, and the scalar number times the b component to give you the vector. So if you're given these two vectors, u is the vector -1, 3, v is the vector 4, 7, and what would be 3 times u, or a scalar 3 multiplied times the vector u? That would simply be 3 multiplied by each component, so 3 times -1 is -3, 3 times 3 is 9. So again, the arithmetic of it isn't that difficult. What is going to be the challenge is recognizing when you want to multiply these, when you want to add these, when you're looking at applying these to a particular word problem. Now, one other thing I want to cover before we wrap this lesson up, or this video up, is how we can represent vectors by adding or using the arrows. And this is going to be very important when you're tackling a word problem, because what you're going to want to do is to make a sketch of what's going on in the problem. For example, you may have an airplane going in one direction with a certain amount of speed or force, and then you're going to have the wind blowing in a different direction with a certain direction and force. What's the result of adding this plane speed and the wind speed together? And so as you draw that out so that you can kind of get a picture of it, you want to know how you do that. To add two vectors graphically, you simply put them head to tail, head to tail. So if we have this vector here and I want to add this vector to it, graphically I can simply take this arrow and put it here. And so I put this tail to this head, and then I end up out here at this point right here. If I now draw a new arrow from the origin out to my new point right here, this is called the resultant vector. This is the resulting arrow that comes about by taking this vector and adding it to this vector. So this is one way to graphically represent vectors being added together. Before I wrap up this video, let me do one example of some of the arithmetic that you'll be doing in your homework exercises. Let's say we're given these three vectors. Vector u has the components -1, 3, vector v has the components 2, 4, and vector w has the component 2, -5. What would be -2u minus 3v? So again, I have a scalar in front of the u and I have a scalar in front of the v. Now there's a couple of ways that you can handle this. You can either multiply the -2 times u and then multiply the 3 times the v and then subtract them, or you could write the components and distribute them. Lots of different ways, so whatever you find comfortable. So I'm going to take -2 times the u vector, so that's the components -1 and 3, and then minus 3 times the v components of 2, 4, and I'm going to treat these vector symbols much like I would parentheses and just distribute these, because in essence when we're working with a scalar, that's what we're doing. So -2 times -1 is +2, and then -2 times 3 is -6. And then I'm going to add these, and I'm going to multiply, or let me do it this way. No, I'm going to do it this way. Add it to, and then I'm going to multiply -3 times 2 here, which is -6, and the -3 times 4, which is -12. And I'm adding here because I'm taking the -3, the negative sign, and distributing it to these. And this is actually plus the opposite of that would be the same thing. Now, if you decided to leave this negative sign, you would distribute to 3, and then you'd have to change the sign. So either way, the arithmetic all works out. Now, to add these components, or these vectors, I simply add the remaining components. 2 plus negative 6 then is negative 4, and negative 6 plus negative 12 is negative 18, so the resulting vector would be the vector negative 4 and negative 18. Yeah, bring that up here, negative 4 and negative 18. Okay, so that kind of combines everything using the scalar, adding the vectors, the components, and then getting your resultant vector.